Okay, so new packet. What we're talking about is more describing relationships. We are looking at another type of graph. So when we say describing relationships in this unit, what we are focusing on specifically is the relationship between two numeric variables. We've already done two categorical. So this is new. We are looking at the relationship between two numeric variables. So I might want to know, what is the relationship between height and weight? What is the relationship between the amount of time that you work each day and the amount of time you spend on homework? Something like that, two numeric variables. When we were looking at two categorical variables, we often looked at that association. Normally we use the word association, but a relationship is the same thing, using a stacked bar graph. So we've already done two categorical. That was a stacked bar graph. What we're doing now is two numeric variables. You're going to notice down here at the bottom of the objective page, there's quite a few things that you're going to learn on the calculator. So we're going to make sure that we have our calculator each day. Okay, so to start out, we're going to start out with an activity that we're going to do together as a class so that we can understand kind of the background of what's going on. Okay, why do we study relationships between two variables? Firstly, we want to be able to make predictions. Maybe we want to explain certain phenomena. There is a whole bunch of different ways that you can refer to x and y. In stats, the explanatory variable, that refers to x. The response variable, that refers to y. In chemistry, in science in general, you've probably referred to them as the independent and dependent variables, right? So the independent variable generally has some relationship to the dependent variable. One of the things that you're going to have to be able to do is, given two variables, decide which one is the explanatory and which one is the response. Do you think if I give you two variables, you can figure out which one is x and which one is y? Are we confident on that? Okay. So when you're making a scatter plot, how do you know which variable to put on which axis? The x-axis is our explanatory variable, or our independent variable. In our case, that was the hand size. We're going to use hand size to predict amount of candy. Y-axis, we're going to put the response variable. And the response variable is what we are predicting. Okay, so where do you start each axis? What is important for us to know about a scatter plot is you don't have to start at 0, 0. You don't have to start at 0, 0. You start wherever you think is appropriate to fit all of the data. And here's why. If we have a scatter plot that we started at 0, 0, like this one here, if I change the axes or the scale or where I start and I move it to up there, that doesn't change the relationship at all. So the relationship didn't all of a sudden get stronger just because I changed where I'm looking. It just helps me to get a better look. Now, on the other hand, do you guys remember with bar charts that we said the y-axis has to start at 0? Right, so if we're looking at a bar chart instead, bless you, we said it had to start at 0. What happens if I started at 5 instead? What was the issue we said if we didn't start at 0? Matthew?
It was misleading.
In what way?
In the way that you can't, everything looks closer or further than they would normally look.
Okay, it exaggerates or minimizes the differences that are there. So in this case, we're going from 10 to about 7. If we showed the rest of the bar, wouldn't it look like a much smaller difference? It'd be much closer. Okay, so bar chart has to start at 0, 0. But scatterplot doesn't or has to start at 0 on your y-axis. Scatterplot, it doesn't matter. When you are making a scatterplot, what do you think you need to include? Just keeping in mind that it's a graph. What do you have to talk about or what do you need to include on any graph? Title. What else? Labels. You're going to need scaling. So on and so forth. We're going to write down one more thing and that'll be it. Okay. So when you are asked to describe a scatter plot, what do you need to talk about? Okay. So if we have one numeric variable, so maybe you're looking at a histogram, a dot plot, something like that. So ignoring the scatter plot for a minute, if we have one numeric variable, so we're looking at a histogram, a dot plot, a stem and leaf plot, a box plot, anything like that, what do you talk about? Come on, guys. CSSU, thank you, CSSU. Now, when you are looking at two numeric variables, there is only one graph. The only graph is a scatter plot. What you got to remember here is FUDs. So we're going to write down what that stands for, and then this will be done. F stands for form. What I care about is the relationship linear or nonlinear? That's it. Nonlinear, you don't have to give me any more information. Nonlinear, curved, anything like that's fine. Don't let 1 or 2 points sway you. So you're looking at all of the points as a whole. You should be able to guess, is unusual. Okay, what could be unusual? Maybe there are outliers. There's no rule. You're just going to do it visually. There might be clusters. That clusters one, something that might be interesting or that is interesting. Do we see how that cluster looks like it has a positive slope? Okay. Do we see how this cluster also has a positive slope? Right? So this one has a positive slope, this one has a positive slope. But then do you see how in general it has a negative slope? That's something you would talk about. Two clusters, positive, positive, but overall they form a negative. Okay, D stands for direction. That's really just slope. And it can be positive direction, negative direction, or none. Again, you're just looking at the general trend. Not every point is going to follow that. And then S stands for strength. Could be weak, moderate, or strong. That just means how close is this to a line. That's it. How close are your points to a line? Like when we did CSSU, a lot of this is just going to be your visual estimation. We're not going to be testing or calculating anything. Last thing I want you to write down is make sure, this is really, really important, you have context and that you use the variable names. You will be reading more about this tonight when you do your reading notes. Okay, so here is the example that we have. The following scatter plot shows the amount of sodium in milligrams and the amount of fat in grams and salads from McDonald's with no dressing. Describe the relationship between sodium and fat. You know, anytime you're describing anything at all, you're going to have context. So I would start with context. Again, we are describing a relationship, not the scatter plot. So I'm going to start with the relationship between sodium and fat for McDonald's salads is, okay, form. Again, your options are linear or not. Not perfect, but it looks like this is fairly linear. So the form is linear. Unusual, we're going to skip for a minute. Direction, positive, negative, none. In this case, positive. And then strength. Strength is how close this falls to a straight line. In this case, our options are always strong, moderate, or weak. If we were just looking at these points and these points, they fall really close to a straight line. These are the ones that don't. So I'm going to call this a moderate relationship. So the relationship is linear, positive, and moderate. So this is a lot quicker than CSSU. We've already done 3 of the 4 things that we need to do. Last thing we need to talk about is anything that's unusual. An unusual point would be one that is radically different than the others. Either it doesn't follow the trend, or like if there was a salad on here that had 2,000 milligrams of sodium, that would be unusual. That would be a really high X value compared to everything else. None of these are unusual. They all follow the trend in general, which is probably about this. What we do notice, though, is that there are 3 clusters. Oh, this point, I guess, is unusual. I don't think that's actually a point, though. That just looks like 0, 0, which means you're eating nothing. So what I would say is unusual is that there are 3 clusters. So we're going to say there are 3 clusters around 200, 600, and 800 milligrams of sodium. I just approximated the X value, and I didn't even do a very good job, but approximated the X value for where those clusters are. That's it. That's the whole description. All you have to do. Any idea why there might be those 3? Like what those 3 relate to in terms of salads?
Menu items.
Okay, it has to do with that.
Would it be like if you got a small, medium, or large?
Okay, great idea. I'm going to tell you they're all the same size.
Like type of salad?
Can you give me more information?
Like the topping on salad?
Okay, what's one topping that often comes on salads?
Dressing.
Okay, we're told no dressing though, but I like the way you're thinking about it. Protein options, right? Protein. What's the most common protein you think that McDonald's is going to put on their salad? Chicken. Okay, what kind of different chickens do we have? Like what kind of chicken can you get on your salad? That's what I mean.
Grilled and fried.
Grilled and fried. So this one represents salads that have fried chicken. This one represents salads that have grilled chicken. And this one has no chicken. You don't need to write that down. It's just a fun fact for you to know. Okay, that's describing the relationship. I'm going to be pretty picky about the fact that you say the word relationship and not scatterplot. We're not describing the scatterplot, we're describing the relationship. And again, I'm going to be picky that you use good context. You don't just say sodium and fat. I have to know that this is McDonald's salads. One thing for us to know is that either variable could be X. In this case, I don't think there's a clear explanatory and response variable. So either one could have been X. Second thing we're going to talk about today is what we call correlation. The symbol for correlation is R. Correlation is a numeric way to measure the strength of a linear relationship. Only linear. You can calculate R for a curved relationship, but it doesn't give us any information. R only gives us the measurement for a linear relationship. Okay, so a few things for you to know. It's always going to refer to two numeric variables. And it is a supplement to help describe the scatter plot. So you would never take a data set, calculate R, and make a conclusion about whether or not the relationship is linear without actually looking at it. Okay, some things you need to know about R. Well, first of all, this is a small thing, but I'm going to tell you anyway. R refers to the sample correlation. What I mean by that is you don't have every single data point. So in this case, we could calculate R for that scatter plot above, assuming that it's a sample of the salads at McDonald's, that it's not all of them. If we had all of the salads at McDonald's, we use the symbol rho. Rho is the population correlation. You're not going to see that symbol very often, but I want you to write it down just in case you do see it. Okay, some things you need to know about R. The first one, R is between -1 and +1. If R is negative, that indicates a negative relationship. So you would see a negative slope. If R is greater than 0, that is going to indicate a positive relationship. So in the scatter plot above, R would be positive because it's a positive relationship. If your R value is close to 0, that indicates a weak linear relationship. There could be a curve, there could be no relationship at all. Again, you don't know unless you look at the scatter plot. If your R is positive or -1, that is a perfectly linear relationship. So all the points fall exactly on a line. Okay, and then the last thing for you to know is that R is unaffected by two things. First one is units. So instead of measuring sodium in milligrams, if we had measured in grams instead, R would be the same. It's not going to change. It's also not affected by which variable is X. Or Y, and that relates to our warm-up. If you switch X and Y, R is going to be the same. Okay. Questions for me? Okay, so let's keep going. Which association is more linear? One with R equal to 0.5 or one with R equal to 0.9? Okay, so what you're thinking here, r equals 0.9 is closer to 1. So that would indicate that that relationship maybe is more linear, but you don't know without the scatter plot. But which one's more linear? Can't tell. You need a scatter plot. So here's an interesting example. You all have seen before y equals x squared. Is y equals x squared linear? What is y equals x squared? If you graph it, quadratic, it's a parabola, right? Very clearly not a line, very clearly a curve. If you look where x is between 1 and 10 on this graph, the r value ends up being 0.97. So between 1 and 10 for x, we get almost a perfectly linear relationship. So that should indicate to you, you have to look at the graph. R is only something to help in addition to the graph. You have to look at the graph first, though. Okay, does a correlation near 0 mean that the association is weak? It means it's weakly linear, but no, could be nonlinear. Again, gotta look at the graph. Okay, is correlation a resistant measure of strength? What do you think? If we have a really wild outlier, do you think that affects the strength of the relationship? For sure. So is correlation resistant? No. And there's two things that could happen. You could have an outlier that's in the pattern or an outlier out of the pattern. And that will do different things to R. Okay, so for example, let's say that this is our data set. We can see it looks like it's moderately linear. Okay, an outlier in the pattern might be out here. So this still follows the pattern, but the x value is very far away from the remaining points. Do you think that this point will make our strength higher or lower? Stronger or less strong? Stronger. Okay, so an outlier in the pattern like that one, R is going to get closer to 1 or -1. It strengthens the relationship. On the other hand, if we have an R that's out of the, not an R, an outlier that's out of the pattern, like this red one, clearly doesn't follow the pattern, that will weaken the relationship. So in that case, R will get closer to 0. Okay, the next question we already addressed, so we're just going to skip it. Next thing to talk about. You have 4 graphs right there. And I want to know which one do you think has the highest correlation? Okay, what do you guys think? Which one has the highest correlation? Or like the strongest? That's really what I'm asking. What do you think? First one? Everybody thinks this one is the highest? Okay, I think it's this one. That would have been my guess. You guys thought the same thing? Did anybody think the third one? Okay, great. Wasn't just me. Thank you. You guys make me feel like I'm crazy. Okay, fun fact. Maybe you connected the dots here. They're all the same. They all have the same correlation. So, what lesson did we learn? You're going to look at the graph before you calculate R. You're always going to look at the graph before you calculate R. Okay. Yes, Veronica.
I have a question.
Sure.
About when you said, the question says, does a correlation near zero mean an association is weak? And then said, no, it could be non-linear.
Yep.
But I thought this was only have correlation for linear association.
So you can measure correlation for any data set that has two numeric variables. Sometimes it's helpful, sometimes it's not. So if you have a curved relationship, you can still calculate R. Like with this one, you could calculate R. It just doesn't give us really any helpful information because the relationship's not linear. Does that make sense? Okay, you want to know the formula? It's a little bit of a doozy. It looks nice, but it's not that nice. So what you're going to do, first of all, you're going to divide by n minus 1. In the numerator, for every single point, you will calculate a z-score for the x and a z-score for the y. You will multiply those two, and then you will sum it all up for all the points. Now, I said it's a little bit of a doozy, doesn't look bad, but what would we have to calculate? Like if we were going to do this by hand, what's the first thing that we would have to do? Or one of the first things?
Calculate the average.
Calculate the average of x, the average of y. Right? That's work right there. Then what are you going to have to do? What else do you need for a z-score? Standard deviation of x and standard deviation of y. Then you're calculating a z-score for every single point. 2 z-scores, really. Right? Every point you're going to have a z-score for x, z-score for y, z-score for x, z-score for y, so on and so forth. Now, I hope you know by now that I'm not going to waste your time like that. So I'm going to show you how to do it on the calculator in a little bit.